We got together and looked at the very first diffraction-limited images that came out of the Webb telescope. And what we collectively saw as a group is we have the highest resolution infrared images taken from space ever. So you think of it as a blob on a picture, but it is extremely high resolution. We have exceeded every expectation. The telescope has performed better than the models said it should. We've even achieved, we talk about resolution and wavefront quality. We've done better in those regards than we thought we would do, and we're just thrilled to death. And to get there, we went through a process. Well, we did the segment identification, and then we formed the image array. And then once they were in the image array, we used this phase retrieval technology to position each of the mirror segments and the secondary mirror itself such that all the optical aberrations were effectively eliminated. We tilt the mirror segments to bring the light from each mirror so that it falls on top of each other at a common point in the middle of the detector. And we call that image stacking. And that concentrates all the light in a single place, but the images, the segments themselves are not cooperating. They're not working together at that point. They're all their own individual telescope. And the next phase in the process is something we call coarse phasing. And that's where we adjust, literally it's the piston. It's the up and down motion of the mirror segments relative to each other. We control the piston of the segments so that they all come together in creating a complete monolithic primary mirror. If you know exactly what the shape of that telescope is, and you know exactly how the light is falling on your detector, it turns out that you can actually prove mathematically that that is enough information to tell you exactly what you need to do to that telescope to fix the alignment errors. And why do we know this? We know this because of something called a pupil imaging lens. And this allows us to take a picture of the primary mirror of the telescope. People have referred to it as a selfie. Right? Well, that's what it is actually. But that's really important mathematically. Now, there's a catch, however. Just because you know a solution to something exists does not automatically give you that solution. And that is the difficult part. That's what we've spent 20 years working out. It's highly mathematical, uses something called Fourier analysis, but that's what we do, is we tease out those solutions and we find what we need to do to each optical element to achieve perfection. We then turn to a different way of doing phase retrieval across the entire aperture of the telescope at the same time. And for that, we're not going to take the telescope out of focus. Instead, we have some lenses that are in one of the science instruments that we use to automatically create a defocused image. And we look at these images and taken as a whole, then we can tell the last little bit of alignment errors that are in the telescope that we need to fix. And that's what we accomplished today. We analyze those images and we apply the corrections leading to the diffraction limit of the perfect performance of the telescope. So there's only one thing left to do, and that's to see how well the telescope is aligned in the other science instruments. And we'll check the alignment there, and if necessary, then we'll apply a solution that optimizes for the entire telescope. We then periodically measure the alignment of the telescope and make corrections as necessary. I cannot wait to see what it discovers.